Hello students, welcome to today's session of chemistry. As you all know, we have started studying 8th lesson of your syllabus, that is transition and inner transition elements. We call them D block and F block elements. Of these two types, we have started studying about transition elements, that is D block elements. And now you are well known to these elements. You know their position, their electronic configuration. We also learned about the variable oxidation states shown by these elements, their physical properties, their metallic character, etc. After studying their periodic trains shown in case of some atomic properties by these elements like atomic and ionic radii, ionization enthalpy, metallic character, in the previous session we learned about three important properties particularly shown by these elements such as catalytic property, color, and the third is magnetic property. And these three properties are particularly shown because of the presence of more number of unpaired electrons in the valence shell of these elements. We have learned about it or those properties in detail in previous session. In this session, we are going to learn about interstitial compounds and their properties, alloys and their applications, physical and chemical properties of D block elements. We are going to learn this much about transition elements. So that means we are going to conclude transition elements in this session. So let us start with formation of interstitial compounds. While studying the first lesson, solid state, you know now what is meant by crystal lattice and how it is formed, as we have accepted that the shape of the atom is spherical. So while forming crystal lattice, these spheres, when they come together to form a crystal lattice, in between there some vacancy or interstitial spaces remain vacant in between the spherically shaped atoms of a metal while forming a crystal lattice. And small atoms like carbon, hydrogen, nitrogen, they get trapped in this interstitial spaces. And because of this, the metal along with these elements is formed, and that is called interstitial compound. Or we will just define that. When small atoms like hydrogen, carbon, nitrogen, etc. are trapped in the interstitial spaces within the crystal lattice, the compound formed are called interstitial compounds. Understood? Now, best example of this is steel or cast iron. That is the interstitial compound formed from carbon and iron. Basically, it is of iron, but the interstitial spaces are occupied by carbon, and together it becomes steel or cast iron. Due to presence of carbon, what happens is the basic malleability and ductility of iron gets reduced, and its tenacity, that is tensile strength, increases. We will see some properties of interstitial compounds, how they differ from original metal. That means the properties of interstitial compounds. They are hard and good conductors of heat and electricity. As we learned that stainless steel, it is harder than that of iron, plain iron, because of the presence of carbon. So their hardness increases. They become good conductors of heat and electricity. Secondly, their chemical properties remain same. They are similar to parent metal because the percentage of parent metal is large enough. Only 0.2, 0.3% of these interstitial metals are there. Hence, the chemical properties remain unaffected. They remain as it is. Their melting points, they become higher than that of pure metals, but their densities are less than that of parent metal. Their hardness increases, hence their melting point increases. The metallic carbides, metallic carbides, that means a compound with carbon of any metal is called metallic carbide. So metallic carbides, the property of metal improves to that extent that it becomes harder like diamond and it becomes chemically inert. So it has tremendous application nowadays. Metallic carbides are nowadays used in various fields and means artificial limbs can be made with carbides because of its hardness and its property of inertness, because it remains as it is and it is lightweight again. Hence, it is used or it has tremendous applications. Hydrides of transition metals are used as powerful reducing agents. Hydrides, metal hydride again, it is metal along with hydrogen. Metal hydrides, as the percentage of hydrogen is more, hence these are powerful reducing agent, that means they bring about a reduction. Example, lithium, aluminum, hydrogen, lithium hydride, various examples are there and they are good reducing agents. So this is all about the interstitial compound and their properties. Now, we are going to learn about formation of alloys. What is the difference between interstitial compound and alloys? Alloys, in interstitial compound, the percentage of carbon, nitrogen, hydrogen, it is very, very, very less, about 0.2%. But in alloys, it is actually fusion of two metals, mixture of two metals, we can say. That means when atoms of one metal are distributed randomly in the lattice of another metal, the metals of or the atoms of one metal are mixed randomly in the lattice of another metal and that becomes alloy. Generally, metals with similar radii, similar properties, they mix with each other to form alloys. There are two types of alloys. That means alloys are classified into two types, ferrous alloys and non-ferrous alloys. Ferrous alloys, first type, as the name suggests, contain iron mixed with another element. So basically iron must be there. When iron is mixed with another metal, then it is called ferrous alloy. Percentage of iron is more in these alloys. For example, there are various types of steel: nickel steel, chromium steel, stainless steel, etc. All steels, they contain 2% carbon. But along with carbon, nickel steel contains nickel, chromium steel contains chromium. And these are all ferrous alloys because iron along with nickel, iron along with chromium, carbon along with iron, all of them contain iron as a main element. So first type is ferrous alloys. Second type is non-ferrous alloys. They are formed by mixing atoms of transition metal other than iron with a non-transition element. That means other than iron. This is the first condition. Hence it is non-ferrous alloy. So any transition metal, when it is mixed with a non-transition element, it is called a non-ferrous alloy. For example, brass. Brass is an alloy of copper and zinc. Iron is not there because it is non-ferrous alloy. Both the types of alloys, non-ferrous as well as ferrous, are industrially very important. They have tremendous applications. Their properties, which are enhanced, can be used in industrial applications. So let us see uses of alloys. First example is bronze. You all are very much aware of this alloy because you see the statues, various statues, you got the medal, bronze medal, etc. are made up with bronze. So what is the bronze? Actually is a mixture. It is actually an alloy of copper and tin. So, only copper, if you use it, gets corroded easily. Hence, after adding tin or mixture of copper and tin becomes bronze, and it is very tough, strong, and corrosion resistant. So the best use of bronze is to make statues. Statues, as we keep them in open air most of the time. So non-corrosion is the need of those statues, and only copper cannot be used. Hence, bronze is the better option. It is strong, tough, and corrosion resistant. So, to make statues, bronze is used. Again, as I told you, medals, trophies, those are also made up of bronze because longer life is needed for these. Hence, bronze is the best option. Next example of alloy is cupranickel. It is an alloy of, as the name suggests, copper and nickel. It is particularly used for making machinery parts of, like marine condenser tubes. Of what? Of marine ships, boats. Their machinery is made up of cupranickel. Marine condenser tubes particularly are made with cupranickel. Again, marine ships, as you know, they are underwater. Hence, again, non-corrosion is the need of these parts, and for that cupranickel is used. Next, stainless steel. This is very tough as well as lustrous alloy. Hence, we use it for domestic purpose to make vessels, but it has the best use for the construction of outer skeleton or outer surface of ultra high speed aircraft. Aircraft, as you know, it is lustrous. That is the first need. What will be the second? That metal which makes the outer surface of aircraft should withstand high friction against air when it goes through air. And for that, stainless steel is the best option because it withstands that higher friction faced by the outer surface of these ultra high speed aircrafts. Again, one more example, nichrome. As the name suggests, it is the alloy of nickel and chromium, of which nickel is 80% while chromium is 20%. It is particularly developed for gas turbine engines. Engines, as you know, this metal alloy withstands higher temperatures. Hence, this is used for making gas turbine engines. One more example, titanium alloys. These again withstand stress up of high temperatures, and hence they are also used for ultra high speed flights as well as in fireproof bulkheads and exhaust shrouds. What are exhaust shrouds? You know, exhaust chimneys, those from where unwanted gases are released in air. So hence, this outer covering of these chimneys, that is called a shroud, it should be made up of high temperature resistant alloy, and that is titanium alloy. So these are some alloys and their uses. Now we will see the common properties of D block elements, in which we are going to see the physical as well as chemical properties. Before that, in your syllabus, in your textbook, study of two compounds such as KMnO4 and K2SCr2O7, that is potassium permanganate and potassium dichromate, is included. In your textbook, it is there, but as the board has declared 25% deduction in your syllabus for this year, particularly because of the situation of COVID-19, so study of those two compounds has been deleted. It is there for CET but not for board exams. Hence, we will conclude now transition elements by studying their common properties. First, we will see physical properties. Now, physical properties, as you all know very well, all the elements of D block are metals. Hence, they show typical metallic properties, such as first one, all these elements are lustrous and shining. Their outer surface is lustrous. They are hard and have high density as they are metal. Hence, they are hard, and because of their hardness, they have high melting and boiling points. As these are metals, they are good electrical and thermal conductors. They have high tensile strength and malleability. As you know, all the metals they are ductile and malleable. One more typical property shown by these elements is they form alloys with transition and non-transition element. That means they form alloy with themselves as well as with non-transition elements also. The many metals and their compounds are paramagnetic. This property we have seen in detail. Again, many of the metals are efficient catalysts. So catalytic properties again typical shown by these metals. So these are the physical properties shown by these elements. Now we'll see the chemical properties. These are typical electropositive metals. All D block elements are electropositive. When we say metals, they are electropositive. That means they are donors. They always form positively charged ions. So these are electropositive metals. They show variable valencies. Valencies, that means oxidation states. And they form colored salts as well as colored complexes. Again, they are good reducing agents. As they are electropositive metals, they are good reducing agents. That means they bring about reduction. Next property is they form oxides and hydroxides which are insoluble. Some metals like iron, cobalt, copper, molybdenum, zinc are biologically important metals. They are used in various biological activities. They catalyze biological reactions. Many of the biological reactions are catalyzed by these elements. So these are the chemical properties of these elements. Now we will see the differences. Differences in between what? We learned in detail about the 3D series or first transition series. So is there any difference between first series and the remaining three series? Very few points are there and which we will study. Although most of the properties are similar, the elements of first row they differ from second and third row in stabilization of higher oxidation states in their compounds. That means when any of the elements shows higher oxidation state in any compound, it is unstable generally. But for example, we will take the example molybdenum with oxidation state 5 and tungsten with oxidation state 6. In bracket I have shown the oxidation states. Their compounds in these oxidation states are more stable. Molybdenum in the second transition series and tungsten in the third. They are more stable than the elements of first transition series such as chromium in its oxidation state 6 and manganese in 8. So, when higher oxidation state comes, the elements of second and third row are more stable. One more difference is the highest oxidation state of the elements of first row is 7. We have seen manganese as shown. Manganese shows from +2 to +7. Highest oxidation state shown by first transition series in which manganese shows is +7. But in case of third row, that means 3D, 4D, 5D series. In case of third row, +8 oxidation state can also be shown in compounds such as ruthenium oxide, RuO4, and osmium oxide, that is OSO4. Understood? So this is all about transition elements. We have to learn about inner transition elements, again extraction, etc. But transition elements or D block elements is complete now. Now, assignment based on today's lecture. You have to define interstitial compound. First question will be define interstitial compounds and give their properties. Second question, give classification of alloys and explain it with example. Next, give physical and chemical properties of transition element, that is D block elements. So these three questions you have to solve. So this is all about today's lecture. I will see about extraction of metals in the next session. So thank you.